Hello, my name is Irving Cardona Camacho. I am from the Department of Electronic Systems at the Autonomous University of Aguascalientes. In this presentation, I will talk about a mathematical model for the propagation of computer devices. The model is called SAEIQRS-T. I will present its analysis and simulation. This presentation is divided in 5 parts: definition of model, equilibrium analysis, calculation of the basic reproduction number using the next generation matrix, discretization using the SAEIQRS-T method, simulations, and results. The SAEIQRS model is a compartmental model. It introduces an extra compartment called T, which represents transmission nodes. They are devices that not get infected, but help spread the virus. Examples include routers or USB drives. The model includes 7 compartments. Susceptible can be infected, antidote, temporal protect, I, exposed, infected but non-contagious, A, infected and actively contagious, quarantine, installed devices, recovered, temporarily immune, and transmission nodes. These are transitions between the compartments from ends to A, antivirus installed, exposed due to contact, protection is effective, infection begins, device are installed recovered, immunity is lost because the antivirus is actualized, change the software, change the system operative. I don't know. From T or to S, the node change is role. Yeah. Each compartment has different equations that describes behavior over time. For example, the equation ds tells us how number of susceptible devices change. Here are the meanings of the departments: B, arrival to the new devices; beta, infection rate; alpha, antivirus application rate; omega, rate of transmission nodes; immunity loss rate; reintegration of T to nodes A; natural exit from each compartment; infection rate of A, and others. This diagram shows all transitions of the model. Solid arrows represent normal transitions. Dashed arrows represent removal of desactivation. This helps you visualize the model full structure. We now study cause where no infection is represented, that is, SAEIQR equals 0. We only focus compartments S, A, and T. We solve their equations by setting the varieties to 0. We start with the equation A, that simplifies because the equations SAEIQR is equal 0, and the equation R that simplifies that term phi1A per I is equal 0, and obtain this equation and solve we get A. The same process for equation T, and repeat the same process for the equation S and substitute T and S. With S calculated, we step into the other expressions, A and D, This is a variables and this is a free equilibrium system. Now, we analyzed the full system. We assume all derivatives are zero and solve for all compartments. We do it step by step. And we start from the first equation S, and take the equation. We have grouped the terms with S and solving for S. Repeat this process for the equation A, equation E, equation I, Q, R, and T. Now, we use the next generation matrix method to compute it to basic reproduction number. We express the system as dx over dt equals fx less ubx, where fx represents the rates of the new infections and ub represents the remains false in the system. Here F represents new infections. We focus in new infecting compartments A, E, I, and R. This is the F vector, which represents new infections in the system. In this case, only the second entry is non-zero, beta Si, from susceptible to exposed. The UV vector includes all other transitions, like antibiotics application, propagation, and recovery. It combines the terms alpha S, phi1, IA, and zeta E, etc., and represents loss from infection states. Here show the Jacobian matrix of if evaluate this free equilibrium. Only the entry relate beta S is not zero. All other partial derivatives are zero because infection only occurs through S and I. Now we build Jacobian matrix of UV. This matrix includes positive sinks and reflects all transitions of infecting compartments. We will later compute its inverse. Now we multiply F by B inverse to get matrix K, which is the next generation matrix. The dominant eigenvalue of matrix is the basic reproduction number. If reproduction number greater 1, the infection spreads. If reproduction number less 1, it dies out. Yeah? This slide shows the formula of reproduction number obtained using Simulink computation in MATLAB. It's a complex expression involving parameters. If quantity, how many infections one infected node can generate. We now apply the non-star finite difference (NCF) method. It converts the difference equation into discrete times equations. NCF preserves properties such as positivity, boundedness, and stability, even in non-linear systems. This is the discrete time version of the equation for S. We calculate S at the next time step, S n plus 1, using current values of R and T and the other parameters. This is MC8 update rule for A. Again, we computed AN plus 1 using AN, SN, and the infection terms with I. The denominator ensures stability, prevents negative values. Same process for equation A, equation I, equation Q, R, and T. We now verify whether the nth method is consistent. We compared exact derivatives with the discretization approximation. If the error tends to the zero, the time step h goes to zero, the method is consistent. This is original continuance of the S equation, writing if contact from we use the computing the difference between the contations and discrete solutions. Here we computed both the local difference residual and discrete residual for S, subtract both expressions, and analyze their difference. After simplification, we find the error is order H, which confirms the method is fits order consistent. This means the solution becomes accurate with smaller step size. The parameters used the model were taken literally. And this produce repeat for all equations. In all cases, is fits order. Proves the NCF method is the first order consistent. The parameters used in the model were the things from literate with specific values to the model difference times malware. Beta is the fast runs or the ransomware on the based on related timing with reference words by Yu, Hu, and Schandiberger, among others. Yep. We simulate three scenarios: fast spreading run, aggressive and rapid infection, runs well, slower and more targeted, undetectable malware, persistent and hard to eliminate. Each and you uses different set of their parameters. In this simulation, we use beta 0.5 and tau 0.05. This represents aggressive infection with the very fast spreads between devices, and the dissimulation using 1000 computings. Sorry. Here we simulated the more controlled propagation and trigger propagation is the ransomware. Then this reflects the tau is equals to 0.08 and the beta is 0.2. On the third case, we use sigma 0.01, alpha 0.005, and sigma 1 0.03. This simulates a virus slow recovery and poor protection with persistence longer. We simulate case 1 using MC8. The trajectory is similar to other 45 with the sharp inflation rather able stabilization. Here we simulated the ransomware scenario using MC8. The spread is lower and reflects the natural trigger attacks. This simulation shows that undetectable virus behaves over time under MCAD. It remains in the network longer with lower recovery and high persistence. Of time, same results on similar results. Simulation case 3 on the other 45 undetectable malware obtained this graphic, and they obtained this graphic on SVD simulation. It's similar result, not equal, but it's similar. The SAEIQRS model is a realistic framework to analyze malware propagation. It includes possible transmission nodes like routers, USB drives, and others. We computed both disease-free and endemic equilibrium. We calculate the basic reproduction number using the next generation matrix. The NC8 method proved to be stable and consistent. The simulations show how different viruses behave and help us design better containment and strategies. These slides list the current reference from recent research. They include compartmental models for the server epidemics and virus propagation over networks. More supporting literature is listed in the word supports to choice departments and methods using the model and simulations. Thanks for your attention.